this video lecture, I will introduce a couple of circuits which are very simple but still quite important. These circuits are the voltage divider and the current divider. Most electronic circuits are designed to perform some operation on signals. This kind of electronic circuits, in general, will feature a pair of input terminals to which the signal to be processed is applied, and two output terminals from which the signal is taken after processing. The input variable may be a voltage or a current. The same for the output variable. The input signal typically comes from another circuit or from a transducer, which is a device capable of converting some physical quantity like an electric field or the temperature or pressure into a voltage or a current. One of the input terminals as well as one of the output terminals may or may not be connected to ground. In its most basic form, a voltage divider consists of two resistors in series. So, resistor R1 and resistor R2 in this scheme. In the circuit, nodes A and B are the input terminals, while the output terminals are represented by nodes C and D. Note that nodes B and D are actually the same node as they are connected by an ideal conductor. The input signal is generated by the voltage source Vs. I will connect the negative terminal of the voltage source to ground here, although this is not necessary for the correct operation of the circuit. So in this circuit, the input variable is a voltage, Vs, while the output variable is again a voltage, and in particular the voltage drop between nodes C and D, the voltage which is called VO. By the way, this voltage drop is also the voltage drop across resistor R2. Our purpose here is to find the relationship between the voltage at the output of the circuit VO and the voltage at the input Vs. In other words, we want to express VO as a function of Vs. In order to do that, let's start by calculating the current I flowing out of the positive terminal of Vs and flowing through resistors R1 and R2. Note that, as I said while introducing the circuit, R1 and R2 are in series, so the same current I flows through both R1 and R2. We already know that two resistors in series can be replaced by a single resistor with a resistance which is the sum of the two resistances, R1 and R2 in this case. And this is what we need to do in order to be able to calculate the current I. So the circuit can be reduced to a voltage source Vs loaded with a resistor Rs equal to R1 plus R2. By applying Ohm's law, we found that the current I is equal to Vs divided by Rs, or Vs divided by R1 plus R2. Now we can go back to the starting circuit and calculate VO by applying again Ohm's law as the current flowing through R2 times the resistance R2. Remember that VO is the voltage drop across R2 here. So now we can replace I with the expression we found before as a function of Vs, and we get eventually Vs times R2 divided by R1 plus R2. It should be apparent here that the value of VO that we got must be smaller than Vs, given the fact that the ratio R2 over R1 plus R2 must be smaller than 1. The voltage divider is a linear circuit. We will discuss about linear circuits and their properties later on during this series of video lectures. Typically, the properties of the linear circuits, meaning the way they affect signals, are expressed through the ratio between the output variable and the input variable. In the case of the voltage divider, VO over Vs is simply given by R2 divided by R1 plus R2. Under some given circumstances that will be specified later on, this ratio is called the frequency response of a linear circuit, in this case of the voltage divider. In the particular case of the voltage divider, the ratio between VO and Vs does not depend on frequency, as R1 and R2 are constant values. The result we have just obtained can be extended to the case of a voltage divider consisting of more than two resistors. Then consider the case of a voltage divider with n resistors, R1, R2, R sub I, Rn. We apply again a signal Vs between the two input terminals. In the most general case, the output signal can be taken across any one of the n resistors making up the circuit. For example, in this case, the output signal is the voltage across the resistor Ri. Again, the current I flowing through the resistors can be calculated taking advantage of the fact that all the resistors are in series. So this current will be given by Vs divided by the sum for j going from 1 to n of the resistances R sub j. By Ohm's law, VO will be given by I times the resistance Ri. Eventually, if we replace I with its expression as a function of Vs, we get for V0 Vs times Ri divided by the sum of all the resistances in the voltage divider. Finally, we get VO over Vs equal to Ri, the generic ith resistance in the voltage divider, divided by the sum of all the resistances in the same voltage divider. In its most basic form, the current divider consists of a couple of resistors, R1 and R2, in a parallel connection. In this circuit, The input terminal are nodes A and B, while the output terminals are nodes C and D. By the way, nodes B and D and C also in this case represent the same node. The input signal will be a current generated in this case by a current source IS, while the output signal will be the current I0 flowing between nodes C and D connected together through an ideal conductor. We can say here that nodes C and D are short-circuited together. As I did in the case of the voltage divider, I will connect one terminal of the current source in the circuit to ground. Again, this is not necessary for the correct operation of the circuit. Since resistors R1 and R2 are in parallel, as I said at the beginning, the voltage across them is the same. Let me call this voltage V. Now we know that two resistors in parallel can be replaced by an equivalent resistor Rp equal to, in the case of the two resistors R1 and R2 in this current divider, R1 times R2 divided by R1 plus R2. So this current divider can be simplified in this way, with a circuit consisting simply of a current source IS and a resistor Rp in parallel to the same current source. If we apply Ohm's law to this circuit, we can find the voltage drop V across the resistor Rp, which is the same voltage drop we find across R1 and R2 in the starting circuit. So by Ohm's law, the voltage V will be IS times Rp. Now back to the starting circuit, we can apply Ohm's law to resistor R2 to find I0. We know V, so we can write I0, which is also the current flowing through R2, as V divided by R2. We can now replace V with its expression as a function of IS, and we get IS Rp divided by R2, or IS times R1 times R2 divided by R1 plus R2 times 1 over R2, which eventually becomes IS times R1 over R1 plus R2. Again, we can say for sure that I0 is smaller than IS, since the ratio R1 over R1 plus R2 is smaller than 1. We can finally summarize the properties of the current divider as a linear circuit through the ratio between the output variable, which is the current I0, and the input variable, the current IS, as R1 over R1 plus R2. Note that the resistance at the numerator in this expression is not the resistance in the branch where I0 is flowing, but the resistance in the other branch. The result we have just obtained can be extended to the more general case where the current divider consists of more than just two resistors in parallel. So consider the case of a current divider consisting of n resistors in parallel, R1, R2, Ri, Rn. We apply again a current source Is between the input terminals. In the most general case, we can take as the output variable the current flowing through any one of the resistances making up the divider. In this case, we will take as the output current the current flowing through resistor Ri. Again, the voltage drop across the resistors V can be calculated taking advantage of the fact that all the resistors are in parallel. So V will be given by Is times the parallel of all the resistances, which is 1 over the sum for j going from 1 to n of 1 over Rj. Now I0 can be calculated as V over Ri or Is times 1 over Ri times 1 over the sum of the reciprocal of all the resistances in the divider. Eventually, the ratio between the output current I0 and the input current Es will be 1 over Ri times 1 over the sum of the reciprocal of all the resistances in the circuit.